Today we're going to talk about phase diagrams. There's two different phase diagrams that we're going to be looking at. We're going to be looking at one that looks like this, and this is the phase diagram for water. We're also going to be looking at the phase diagram for all other substances, but we're going to use carbon dioxide as that example. So let's talk about what this phase diagram is telling us. If we look at our axes, we have pressure as our y-axis and temperature as our x-axis. Pressure can be in four different units. ATM, which is atmospheres, kPa, which is kilopascals, torr, or millimeters of mercury. All of these can be found on the front page of your reference packet. On the front page of your reference packet, it tells you the conversions between them. Those are all when it's at your atmospheric pressure, so normal pressure. For atmospheres, it's at 1. Kilopascals, it's at 101.3. Torr, 760. And millimeters of mercury is also 760. These are numbers that you need to know, but again, they're in your reference packet for you, so you don't necessarily have to memorize it. Now our temperatures, here we have it in degrees Celsius, but it also can be in Kelvin, never in Fahrenheit. So let's talk about what these lines tell us. Here we're talking about phase diagrams, so we're looking at our different phases of matter, so our different states of matter. We have solid, liquid, and gas. Make sure you know the places that solid, liquid, and gases go. As we go across these lines, we're doing a phase change. But on the lines, these are our equilibrium lines. So if we look at the line in between solid and liquid, this is where we have the same amount of solid and liquid at that specific pressure and temperature. So what we have to do is make sure we understand, if we're going across this line, what phase change are we going through? So if we're going from solid to liquid, we are doing melting. If we're going from liquid to solid, we are freezing. Now it's also important for you to realize which direction is going to be exothermic or endothermic. Melting is endothermic. Freezing is exothermic. Now let's look at our equilibrium line between liquid and gas. As we go from liquid to gas, this is called evaporation. As we go from gas to liquid, this is known as condensation. Now evaporation is going from a liquid to a gas, so this is our endothermic reaction. Not a reaction, our phase change, sorry. Condensation is going to be exothermic. You probably know the names of those four different phase changes. But what we need to do is also know the names of the phase changes from solid to gas and gas to solid. So as we go from gas to solid, this is called deposition. As we go from solid to gas, this is called sublimation. We need to also know whether these are exothermic or endothermic. So going from a gas to a solid is going to be exothermic. Going from a solid to a gas is going to be endothermic. So you need to know all of those different phase change and whether they're exothermic or endothermic. Remember, exothermic means you're giving away heat. So if the substance you're going to moves slower, then in order for it to slow down, it needs to give away its energy. If the substance you're going to, the particles are moving faster, you need energy taken in so that those particles can move. So those are our different phase changes. Now I'm going to erase all the phase changes so that we can get back to these other points that I've put on here. so that looks a little bit cleaner now. Notice I have 4 different points. You need to know what each of these 4 points are. Let's start with our triple point. Notice our triple point is when all the lines come to one point. So our triple point is when all phases of matter are in equilibrium. Make sure you write that definition down. Our triple point is when all phases of matter are at equilibrium. So all 3 are present. Our critical point is on our equilibrium line for liquid and gas. It is the point that no matter how much you increase the temperature, you cannot convert liquid to a gas anymore. So our critical point is the point where we don't have liquid, we do not have gas. We have something called a supercritical fluid. So that's above our critical point. Our supercritical fluid has both properties of a liquid and gas, but it's not really either. That's our critical point, triple point. Now, notice how I have normal melting point, normal boiling point. When we say normal, we're looking for atmospheric pressure. Atmospheric pressure is going to change depending on the unit that we're talking about. This graph is in atmospheres. So our normal pressure is going to be at 1 atmosphere. So if I want to know the normal melting point, I go to 1 atmosphere, go over to the equilibrium line between solid and liquid, because that's where melting occurs, and then at that temperature, if I were to bring it down on my graph, this is the temperature that your normal melting point occurs at. Same thing for normal boiling point. Again, I have units of atmospheres here, so I go to 1 atmosphere, come over to where boiling occurs between liquid and gas, and follow it down. This is the temperature of my normal boiling point. So like I said, we're doing 2 different phase diagrams. We're doing one for water, and we're doing one for basically every other substance, which we'll represent with carbon dioxide. Now this is a water diagram. A water diagram has the equilibrium line between solid and liquid having a negative slope. So it's sloping towards the pressure axis. Now, the reason why this is going to occur has to do with the fact that solid water is less dense than liquid water, which is only true for water. All other substances have a solid state of matter that is more dense than the liquid state of matter. So now let's try to process this. So if we are at the same temperature, but we're increasing pressure, pressure means you're condensing something. Now, our solid, we said, is less dense. So that means that its particles, not that they're more spread out, but they're not as tightly, not really as tightly held together. So if we think about our liquid having more density, as we increase pressure, we should be going into our liquid phase as opposed to our solid phase. And that's what this line having a negative slope tells us. Now, if we were to draw a diagram for a different substance other than water, so carbon dioxide, for instance, as we increase pressure, we're going into our solid phase, which would make sense because our solid is more dense than liquid in all other substances.